Well, hello, ap1. If this is working properly, you're watching and listening to a video. We're starting today on page 438 of your textbook. We're going to do section 13.5, motion of a pendulum. All right, so let's give this a whirl here. The idea here is to show you that a pendulum is an object that will undergo simple harmonic motion. Pendulum's just going to be any mass dangling and swinging on a string of some sort. So you can see what I've drawn here so far is a pendulum. The vertical dotted line is our equilibrium position. Pendulums in equilibrium hang vertically, so that's the equilibrium position equivalent to a spring's. I have moved this pendulum a distance s from the equilibrium point, and I'm ready to let it start swinging. Now, the pendulum's going to have a length L, okay? So from the ceiling to the mass is the length L, and given the definition of a radian, that tells us that our angle is just going to be the ratio of S over L, okay? Now, what else do we have here? Well, that mass is attached to a string, and there's going to be some force of tension in that string, and vertically speaking, there's going to be some force of gravity. The combination of those two forces will be some force in this direction, and that force in that direction is the restoring force for a pendulum. That is the force that we want to compare to a spring. Okay. Now remember, a spring involves simple harmonic motion, and for simple harmonic motion, we're looking for a force that is proportional to a displacement. So is this force proportional to a displacement? That's what we have to find out. So let's go find out what that force is. Okay. Let's draw a free body diagram for that mass. Okay. Free body diagram for the mass on the pendulum. We would have force of tension that way. We have gravity this way. Let's make this the y-axis, and let's make this the x-axis. So there's x and y. Okay, there's my angle theta. So what do we have? Well, the tension force will cancel out with the gravitational component on the y-axis, which is adjacent to my angle, so mg cosine theta. So that one and that one will cancel out. That leaves just my x component here, my x component of gravity, which would be opposite the angle, so mg sine theta. Okay? If the vertical tension force and the vertical gravitational force cancel each other out, only the x component gravity is left. That's this. So our restoring force is that. So for the pendulum, our restoring force is mg sine theta. Okay? Now if you go back to our pendulum, you can see that the force and the displacement are in the opposite directions. I displace to the right, the force is to the left. They're in opposite directions. So we should include a negative sign here, okay? Let's continue on down here. Oops. Over to the next page. So, theta is S over L. So the force is negative mg sine S over L. Okay? Now, for a force to be in that which would provide simple harmonic motion, we would want, as in the spring, negative kx, where we have some constant times displacement. Here, our force is proportional not to a displacement, but proportional to the sine of a displacement. Remember, S is our displacement. So that means, in general, pendulums do not exhibit simple harmonic motion. However, it turns out for small angles, if theta is small, and by small we mean less than 15 degrees, then as it turns out, and this only works in radians, but it turns out sine theta is approximately theta if the angle in radians is less than 15 degrees. So that means that if we talk about a small angle for the pendulum, that sine of S over L is going to be approximately the same as simply S over L. So if our angle is small, the pendulum is going to exhibit simple harmonic motion. Let me show you. Because we would take our equation, negative mg sine of S over L, but now sine's replaced with just S over L, so that gives us mg over L times S. mg over L times S. So we've got a constant times a displacement. That gives us simple harmonic motion, a constant times a displacement. The force is now proportional to a displacement, S being the displacement again. So for small angles, pendulums do exhibit simple harmonic motion, okay? Now, that means that because a pendulum for small angles exhibits simple harmonic motion, a pendulum would have an angular frequency of 2 pi times its frequency. Remember, for a spring, we said that that was the square root of k over m, where k was the spring constant, okay? So that was k, that was for a spring, where k is the spring constant. Well, if we look at this equation, and we compare it to the equation for a spring, then we have a constant times a displacement there, which means here we have a constant mg over L times a displacement. What I'm trying to say is, for a pendulum, k would be, and I just got myself all confused, k would be mg over L in that example. So omega would be mg over L divided by m, all square rooted. M's cancel. So for a pendulum, omega would be simply the square root of g over L. Right? But omega is also 2 pi f. And f is 1 over the period. So omega is going to be 2 pi over the period. Which means the period is simply 2 pi over omega. And omega, we just learned, for a pendulum is this. Right? So the pendulum, omega is the ratio of g over L square rooted, and the period is 2 pi times the inverse of that. So for a pendulum, the period would be 2 pi times the inverse of omega, which would be this. This gives us the period of a pendulum. Notice that the period of a pendulum does not in any way depend on the amplitude of oscillation. It does not in any way depend on the mass of what's hanging on the pendulum. Pendulums are driven by gravity, so it should make sense that it's not going to be dependent on mass. All right, let's see if we can look back at your textbook here. At this point, I would like you guys to look at Quick Quiz on page 440, Quick Quiz 13.8. A pendulum clock depends on the period of a pendulum to keep the correct time. Suppose a pendulum clock is keeping correct time and then, silly, Dennis the Menace slides the bob of the pendulum downward on the oscillating rod. In other words, he made the pendulum longer. He increased the length of the pendulum. So, if I increase the length of the pendulum, does the clock run slow, fast, or correctly? I've answered the question there for you. I want you guys to spend some time thinking about how that makes sense. For Quick Quiz 13.9, the period of a pendulum is measured to be t on Earth. If the same pendulum were set in motion on the moon, would its period be less than, greater than, or equal to? Well, what's different about the Earth and the moon? Well, the difference between the Earth and the Moon would be g. So if I change g, what happens to the period? And in the previous problem, if I changed L, what happened to the period? All right, so there you go. At this point, you guys should be able to handle homework problems 1, 7, 15, 27, and 30. So get on those. At this point also, I think for today, what I would like you to do is play around with example problem 13.7. Go through exercise 13.7, the answer's there. Let's see if we can get this all done.